because I will need some compactification hydraulics, because I will need it later to discuss certain dualities in 6 dimensions. Okay, so maybe I will just mention what's going to happen. So in the dualities, 2 different string theories will be related to each other, provided of course they have the same supersymmetries, right? I mean, you cannot relate one string theory, which I say n equal to 2 supersymmetry, to another string theory with n equal to 1 supersymmetry. That won't be possible. But what you do is you relate different string theories with same amount of supersymmetry. Now, type 2A and type 2B both have n equal to 2, but one is chiral, other is non-chiral. So they will not be related directly to each other. By some other operation, by some T dualities, you can go from type 2A to type 2B, and then you can relate that. That is a lower dimension. But if you want to relate, so this way you see immediately that you cannot relate type 2A or type 2B to heterotic or type 1 string. Because heterotic and type 1 have n equal to 1, right? N equal to 1 in 10 dimensions. Whereas type 2A and type 2B have n equal to 2. So if you want to relate these 2 theories, these 2 sets of theories, you need to somehow break half of the supersymmetries starting from type 2A or type 2B, right? So this happens when you start compactifying on some curved spaces. In general, you can break, right, depending on the choice of your space. Okay. So the first non-trivial example, at least historically, the first example which came about was by looking at type 2A compactified on a K3 surface. K3, I think George mentioned briefly in his lectures. So K3 is a 4-dimensional, real 4-dimensional manifold with certain properties. So when you compactify type 2A on K3, it breaks half the supersymmetry. So the resulting 6-dimensional theory will have half the, so initial supersymmetries, okay, so it's like n equal to 1, say, if you count it in terms of 10 dimensions. So this means 16 supercharges. On the other hand, heterotic theory compactified, heterotic theory is already n equal to 1, right? So you don't want to break further the supersymmetry of heterotic theory. So you must compactify on flat space, which is a torus. So for this reason, what I will do is I will do a toroidal compactification of heterotic theory. Nothing complicated, just torus compactification. But then I will, later on, perhaps that will be the last lecture, then I will try to relate the 6-dimensional type 2A on K3 to heterotic on T4. Okay. So for this reason, I will do that. So it's a little bit, I'm still not entering the dualities yet, but I'm just preparing the kind of basic ingredients I need to discuss dualities. So yeah, so we'll discuss the toroidal compactification of heterotic. I mean, most of the things I've been talking about, actually, this you can also apply to type 2A and type 2B. That is not so important, but specifically I'll be looking for it. So let's suppose I start from 10-dimensional theory. I compactify on some d-dimensional torus. And you come down to 10 minus d dimensional in Minkowski space. So we have 10 minus d-dimensional Minkowski space. So when you compactify this, okay, as we have seen many times, the d-dimensional torus can be written as Rd divided by gamma d, quotiented by gamma d, where gamma d is of d-dimensional lattice. So this guy is d-dimensional. And now we can do the, everything is flat, so nothing particular happens. You can do the same mode expansions for all the x's. So what we have is x. So I will write down the indices. So we'll have, so the 10 minus d-dimensional, the Minkowski space type, I will use the index mu, etc. Right? So these indices will be, these are the indices, directions in the Minkowski space type. 10 minus d-dimensional Minkowski space type. Okay. In the d-dimensional torus, or in this Rd, I will use the indices I, j, etc. So these are running over the d-dimensional torus. And finally, on the heterotic side, for the heterotic theory, you have the right movers. Those will be the extra right movers, the 16 right movers, right? I going from 1 to 16. Capital I. So this is small i's. Mu. So the mode expansion for the mu's, nothing happens to that. It remains the same. You have the little x mu plus, I mean, this is the zero mode, the average position. And then you have p mu p. Again, I will not be keeping track of alpha primes and so on. That's just, you can put them by dimensional basis. And the oscillator modes. For the xi, now it's these are compact. So in general, I can write this as some t left times t plus sigma plus t right I t minus sigma. This, you remember that when you compactify, the coefficient of sigma are the winding modes and coefficient of t are the momentum, but both are quantized, right? Because it's a toroidal. And I just regrouped them in terms of t plus sigma and t minus sigma, right? Because t plus sigma is the left moving part and t minus sigma is the right moving part. And so I just regrouped them. The Caruso-Klein momentum and the winding modes, I've chosen some combinations to write this. Plus the oscillators again. And then finally for the xi, we have little xi plus, now it's only a function of, because these are only right movers, remember these are only right movers. So they are only functions of t minus sigma. So I have t on I. T minus sigma plus the oscillators, but now the oscillators have only the right moving part. Here in both of these cases, there are both left moving and right moving oscillators, but here this is only right. So this is the structure, and one can again write down the partition function like what we did for the 10-dimensional heterotic string. So you'll have again trace to q to the F0, q bar to the F0 tilde, where now let's write down what is F0 and F0 tilde. L0 will be, you have half p mu square, again there are alpha primes and so on, plus half pi L square. You see, this is the left moving part, so you're only taking care of the t plus sigma part, right? Derivatives with respect to t plus sigma. So you have that, and plus the oscillator modes, minus half or 0, depending on whether it's Lewis Schwarz or not. This oscillator mode is again, you have both the contribution of boson, I mean the x's and psi's. So it has the oscillator mode of bosons plus fermions. Because left moving sector is a fermionic string. Right? I'm not focusing so much on that because I'm really focusing on what I want to look at is the conditions on the corresponding lattices. Because you see, these are discrete, these are quantized. Both of these guys are quantized. This is quantized. So altogether, they are in some lattice. And again, I'm trying to focus on the lattice. What kind of lattice we can have. And then you have L0 tilde, which is half p mu square again, plus half, I mean there are alpha primes. Okay. But here you remember I have already absorbed alpha prime inside. So in writing these objects, I have already absorbed alpha prime inside. Okay. Plus PR I square plus n tilde minus 1. And again, this is oscillator number, and this minus 1 is simply because we are talking about the bosonic string, so the normal ordering term is minus 1 for the bosonic string. Sorry, I forgot this marker. Because we also have this P line I in that part. Plus So in fact, you can think of all of these, which are all quantized. I can think of this as living in some lattice. So some gamma, so how many dimensions of lattice? This is 16 dimensional. This is d-dimensional because the little I goes over the d-dimensional torus. So this I goes from 1 to d, small I. This also goes from 1 to d. So this lattice is 16 plus 2d dimensional. 16 plus 2d dimensional. But I will write it in this way, d comma 16 plus d, to remember that this d is a left moving part and the remaining 16 plus d is a right moving part. But the total dimension is 16 plus 2d. So this is a lattice. So in other words, we are saying that this vector is pi l, pi r, comma p capital P capital I R. This big 16 plus d dimensional vector belongs to some lattice, which I denote by gamma d comma 16 plus d. All right. So now let's go back to this.
Excuse me.
Yeah.
I'm a little bit lost. Could you repeat why the capital I index goes from I to 16?
1 to 16. No, sorry, did I write 1? No, 1 to 16.
Could you repeat 16? I lost.
Yesterday, you remember we did the heterotic state in 10 dimension, right? So in 10 dimension, what we had, so no compactification here. So d is equal to 0, right? So that's what we did there. And we had, so the left moving part was a fermionic string. And so it is a critical dimension is 10. So we had x mu, 10 of the x mu's, and the corresponding fermionic partners. Right? That was the left moving the content.
Excuse me, Professor. Could you write a little bit bigger?
Yeah, okay. Okay, so I'll write now. Can you read this left moving part of the fermionic? Left moving was a fermionic sector, and it's the variables were x mu, the bosonic, the positions were x mu, I put here left, to indicate it's left, and the fermionic partners psi mu. Okay, and the right movers was a bosonic string, and it had critical dimension 26, right? So I split it like this, x mu, right, and xi, capital I, right? So these are 10 of them. Mu is over the 10-dimensional Minkowski space, and then there's extra 16. So this capital I goes from 1 to 16. Then you combine these two things together to get the standard 10-dimensional coordinates, x mu, which has both left-moving and right-moving part, and then these guys which are only right-moving, right? So now I'm compactifying this part on a d-dimensional torus. So this index now splits into two categories. One where this index runs over 10 minus d, the non-compact Minkowski space, right? So that I indicate by mu. And then those indices which go over the d-dimensional torus, I label by ing to distinguish between the two sets. Okay. So that's why, so there are the 16 sets. So we have this momentum lattice, and now we can find what is the partition function.
So the theory is in 36 dimensions.
Sorry?
The theory is in 36 dimensions, and you usually have 16 that are like confined, but in the fermionic there doesn't leave any.
You mean here, left moving
Yeah,
part?
because in the left moving you have
10 dimension.
Right, you have 36 dimensions.
Yeah, exactly.
As you
Yeah, that was the point. That was the point. I mean, these are the non-compact part is purely, 10-dimensional x mu, but this is some kind of internal variable which is purely right movers. It has no geometric meaning because for geometric meaning you must have both left and right movers, right? But
it's just in order to cancel the
exactly. I think in Ana Maria's lectures, she will, instead of using these coordinates, xi, she will use the fermionic language. So you know that in 2 dimensions there is something very special happens. That a boson can be expressed, it can be fermionized, or vice versa. So one boson can be written in terms of 2 real fermions. So Ana Maria will use the fermionic language. So where anyway there is no geometrical But this is sometimes it's more convenient to work with the bosonic variables.
Sorry, then you start in a 26-dimensional space. You say bosonic modes, and then
No, it's not 26-dimensional space. The space is very 10-dimensional. These are the non-compact spaces. Right? X mu is non-compact. This extends from 0 to. This guys, you see that. I mean, this is, you really cannot think of it geometrically. I mean, there's not some geometric object, geometric directions, because there's only right movers. There is no geometric significance. It is just to, as you're saying, that it is just to cancel the lines. You need to have some additional sect here. I mean, this will only give 10 central charge. Central charge will be equal to 10 for the 10 coordinates here, right? 10 coordinates. You need something else to contribute the extra 16 to cancel the anomaly. And that is, okay, this is one language. I just use the bosonic language, but you don't need to. You can use fermionic language, in which case each of these bosons fermionized as 2 fermions. So you'll have 32 fermions. Okay. So this, you shouldn't think geometrically. Indeed, you see geometry, because you see that this lattice, remember, was self-dual lattice. Okay. Now, the coefficient of sigma is the winding mode, right? Coefficient of t is the momentum mode. So suppose if you think of some radius r, the winding mode goes like r, whereas the momentum mode goes like 1 over r. But this is self-dual lattice. This is self-dual. So essentially, roughly speaking, r is of the order of root alpha time, of the order of string scale, right? And in such distances, you don't have a geometric meaning. That's one thing that we have learned from string theory. That at such distances, you cannot think geometrically. Geometry itself emerges as a long distance phenomenon in string theory. Distance is much larger compared to the string scale. That is where you have a geometric motion. Otherwise, it's a mess. I mean, inside we don't know what is happening. But what we have is a good polynomial field theory description. I mean, there are many examples of that. For example, I don't know. In fact, yes, I think Clifford. There was a question during Clifford's lecture. What happens to the self-dual radius? No, when r equal to root alpha prime, right? What happens there? So maybe I will discuss this here. Okay, let me just postpone that for a moment. Maybe I will discuss it. What happens at the particular radius? All right. So this is the situation here, and now we try to look at this partition function, and so partition function will be this. Okay, there is a d2 tau, t tau, etc. So this q to the s0 will be okay, whatever it is, q to the okay. Let me go. So there is a half t mu square. Okay, I don't have to write it. Anyway, the expression is there, so we don't need to write that. So there is q to the L0 and q bar to the L0 tilde. But from there, I want to focus. No, I want to focus on the whole thing. I want to look at the lattice part, right? So q to the power of the half to mu square plus n minus half or 0, depending on the Schwarz or Ramon. Okay. This intercept is different for the two sectors. And then I want to separate out explicitly the lattice part. So there will be something which is q to the power of half PL I square. And similarly, you have q bar to the power of half P right I square plus half P right capital I square. Right? So that is what the lattice part is. So here there is a lattice part. So this momenta P left I, P right I, P right I, P right capital I, all of this belong to T comma 16 plus D. So that is the lattice part, and then the remaining part, you have q bar to the power of half P mu square plus n tilde. And I have to take the, so the trace, this is a trace over the lattice momenta, because when you take the trace, you have to sum over all the states, right? So in particular, states are labeled by the lattice momentum. So this is a trace over the lattice momentum. Here, I have the, what are the other traces? This is something I didn't mention yesterday. So let me just spell it out clearly. So here, you have the sum over the Fock spaces, the left and right Fock spaces, because as n and n tilde refer to the oscillator creations, no? So you have to sum over the Fock space. So that's the Fock space. And you also have to integrate the p mu. P mu are continuous variables, right? These are non-compact directions, so momentum p mu can be anything, any real number, right? So I need to also integrate over d p mu. And how many of them are there? This is 10 minus d dimension. So this is what the trace means. So all that. This integral is very trivial because the p mu is just Gaussian, right? So this can be immediately, look at the p mu dependence, it's e to the power of I by tau minus tau bar p mu squared, right? Tau coming from here, tau bar coming from there. So that just gives you, this integral will just give you, the result of this integral will be 1 over in tau.
Bigger, please.
So yeah, I mean, okay. So e to the power of I by tau minus tau bar times p mu squared, right? That is, I've just combined these two parts where the p mu appears there. So that is this part. So this is just a Gaussian integral, and you will just get 1 over in tau to the power of 10 minus d divided. So that part is trivial. Then you have the Fock space part, which is a bit more non-trivial, and I don't know if you have seen it in Carmen's lectures or Martin's lectures. But I mean, I will not need it, so I'm not going to work with it, because that will take some time. It will take me out away from the discussion of the molecules. So not discuss that. I mean, there's a lot of beautiful story here in this Fock space sums. You get all this beautiful theta functions and Dirichlet data functions, which are very nice modular properties, but I don't have time to write. Now look at this lattice. Let's again look at this lattice sum and ask the question, it's the modular transformations. So modular gradients and modular transformations. So we said yesterday that this modular group is generated by two transformations. One was a tau going to tau plus 1, and the other was tau going to minus 1. Okay. When you make the first transformation, that's very easy, because q goes to q times e to the 2 pi I, and q bar goes to q bar times e to the minus 2 pi I, right? Because remember q was e to the power of 2 pi I times tau, and q bar was e to the power of minus 2 pi I, just the complex quantity of that, tau bar. So when you make such a transformation, you see that each of these terms inside the lattice sum picks up e to the power of I pi p left square minus p right square. And when I write this now, I'm just writing as some kind of vectors here. So this p left is just d-dimensional, and in this p right, I've combined all of this together, because it's all right moving part. Okay, so this whole thing I'm writing as p right vector. So p right is p right vector is all of this p right I, small I, p right capital I. So this is 16 plus d-dimensional. Okay? This is 16 plus d-dimensional, whereas this p left is just d-dimensional. So you find this phase for each of these terms. So if you require modular invariance under such a transformation, that just says that p left square minus p right square is an even integer. But the important, yesterday also we saw in the 10-dimensional discussion that you had this condition that p right square must be even integer, right? But now we have a p right left square minus p right square. So this is a, you see the signature here. This has a Lorentzian signature. So if you think of this entire 16 plus d, 16 plus 2d dimensional vector, this whole thing, which is 16 plus 2d dimensional vector, lattice vectors, then the inner product, or the inner product that appears here is with the negative signature. is a Lorentzian metric. Okay. So what we are seeing here is that, I think I can erase this now. So what we see here is, so this, there is an inner product. So there's an inner product which has a plus signature for the P left part and minus signature for the P right part, or the right moving part. Both of these together, which I'm calling as P right. So with this metric, this quantity is nothing else but the norm square of the P vector, right? But with this signature. So it's a Lorentzian signature. So what we are seeing is that with this signature, this lattice must be E1. Then what about the second transformation? That was what we discussed in detail last time. Tau going to -1 over tau. And I will not repeat those steps. Those steps are almost identical. And the result will be, finally, just like yesterday we saw that this transformation implied that gamma is self-dual. Right? The same thing happens here. What we have is gamma d, 16 plus d is self-dual. But again, self-dual with this metric. With this metric. Because the notion of self-duality has, you need to know what is the inner product. Right? So that inner product is again calculated with that. This is not a physical metric or anything like that. It just appears in this computation. It's not that I'm having multi-time directions. It's not that. It's just that this happens and this appears in this calculation. So we have so the condition finally combining the two, this transformation which told me that this lattice is E1 and self-dual. So what we have is that this lattice is self-dual and E1. And yesterday I told you a theorem, the mathematicians have proven a theorem, that in general if I take a gamma p comma q lattice, where there are p number of positive signatures and q number of negative signatures, such an even self-dual lattice exists if only p minus q is equal to a multiple of 8, the integer multiple of 8. Right? And this is the interior case, because the difference between the two, between this p and q is 16, which is a multiple of 8. So such lattice exists. Okay? And then the second statement was that when both of these p and q were not 0, there was a unique lattice, unique such lattice, but of course up to the symmetries of this metric. The symmetry of this metric is what? Is SO B, or more generally O, orthogonal, B, 16 plus D. Right? This is a Lorentz group. With the, let's say, think of this as so many time directions and so many space directions. So this is a Lorentz transformation, which leaves this metric invariant. So you have a unique lattice up to such transformations. But now we want to ask, when I make such a transformation, suppose I start with one of the lattices, one given lattice which is even self-dual, and I start making such a transformation. Right? What this theorem is saying that any other lattice I can obtain by such a transformation. So let's see what happens when I start making a transformation with this. Question is, do I get a different physics or not? Do I get a different spectrum or not if I make such a transformation? But now let's look at the spectrum. Oh, I just erased that formula. But the spectrum was given by L0 was various other things. I mean, okay, you have the mass square, given with some number, plus n, plus half p right square, minus half or 0, depending on Navier-Stokes amount. And L0 tilde was again m square, the same number times m square, plus m tilde minus 1 plus 1 p left. So this is p left and p right square. So this was it. Now when I make the Lorentz transformation, what do they do? They take p left, p right to some p left prime, p right prime. Right? When you make a whole d, 16 plus d transformation, you will take this to some other vector. Right? Now, if you make I mean, if you make kind of just a rotation in the time directions, so in other words, OD, nothing on 16 plus D, then nothing changes because that is just going to rotate only the PL within itself. It won't mix PL and PR. Right? If that happens, nothing changes the spectrum because P left square will remain invariant. Right? Similarly, if you do a rotation only on 16 plus D directions, nothing changes because it only rotates the P right, it will mix, and P right square doesn't change. So spectrum doesn't change. So what we have learned is that pure rotations in the so-called time directions and the pure rotations in the so-called space directions do not change the spectrum. You get the same theory, nothing happens. Right? However, if you make a boost transformations, boost type of transformation which mixes these two, then you see the spectrum changes. Right? So the conclusion is that the different, let's say, different compactifications, different inequivalent compactifications, well, not exactly inequivalent, but let's say different compactifications are labeled by this group, modeled by the subgroups OD times O16 plus D. Right? So what we are seeing, what we are saying from here is that, so what we say that the OD subgroup of OD comma 16 plus D, and more generally OD times O16 plus D does not change anything in the spectrum. Right? So the different spectra will be obtained when you look at, are labeled by this coset space, OD cross O16. So when you make these are basically the boost transformations. Right? So such transformations will change the spectrum, and so therefore you are getting a different compactifications. Right? So this is a very quick way of finding the entire moduli space of toroidal compactifications. If you take a d-dimensional torus, then the moduli space of all possible such compactifications is given by that. Actually, it's not quite this, because whenever you have a lattice, you can choose. You have always this freedom of choosing a different basis. Okay, you remember like SL2Z you mentioned. So in this case, really, you should also divide by the discrete group, which is this guy, but with the coefficients being integers. Because this corresponds to just choosing different bases. They don't change the lattice. We're just choosing a different basis. So this is the actual moduli space. This is in fact the moduli space of d-dimensional compactification on the torus. It's only for torus. So, okay. Now, what is the dimension of the space? The dimension of the space will be, of course, the dimension of this space minus the dimension of what you're quotienting. Right? The dimension of this space is simply d, let's say d plus 16 plus d times d plus 16 plus d minus 1. So this is the orthogonal group, right? Divided by 2. That's the dimension of this space. The dimension of this space. And the dimension of these spaces is d times d minus 1 by 2. That is the dimension of this space. And the dimension of that space is 16 plus d times 16 plus d minus 1 divided by 2. And I have to subtract this, right? The dimension of the numerator space divided by what your dimension of what you're quotienting. So that is the dimension of this space, this quotiented space. And when you do this calculation, if I have not made some mistake, you'll find that this is equal to actually, what is it? I think just d times 16 plus d. Maybe you should just check. So that's the dimension of this space, d times 16 plus d. Is there any question up to this point?
The momenta are quantized, right?
All the momenta are quantized, yeah.
But if you still perform a continuous all information, the performance
No, just give you different momenta. So I mean, momenta are quantized in what unit? Radii, So you can change the radii, of course, in a continuous way. So this is telling you roughly how many different radii. I mean, different choices of radii correspond to different compactifications, right? But here it's not just radii, because radii would be only d of them, right? But you have the angles between the different bases, plus something else. In fact, I'm going to interpret. I'm going to give you an interpretation of what these parameters mean. Okay? Some of these parameters will be like radii, but there are more parameters than that. This, by the way, the reference for this entire work is, I don't know, 1985 paper, I think 85, which was written by me, I think physics letters, in physics letters, PI. I don't remember the precise numbers, physics letters. And the interpretation of these parameters is in another paper, which was, I think, in 86, I'm not sure, 86 or 87, I'm not sure. This was written in collaboration with Kumar, Richard, and myself. So these two papers basically summarize, I mean, the details of it.
Narain,
Yeah.
this is lattice, this is the so-called Narain lattice.
I just call it Lorentzian lattice.
I mean, that's the, when they made it, is the text.
Okay. Yeah, so, but one more thing I wanted to say. You have seen the GSO projection last time. Since I have this this modular transformations here, before discussing the interpretation of those parameters, let me just mention one thing. You have seen the GSO projection last week, right? And I don't know if Carmen explained to you that GSO projection was necessary. Or some kind of GSO projection is necessary for consistency of string theory. Because, I mean, one may think that, okay, we do the GSO projection to remove the tachyon, right? Or to get supersymmetry, right? But you can ask, why should I do that? No? It looks a little ad hoc, no? Because you want to get something, so you do something, no? Okay, but actual situation is much more restricted. I mean, the string consistency itself tells you that there must be something like a GSO projection. It's a little bit more general than what Carmen did for the superstring. You can allow some more possibilities, but not too many. There are just a few, 2 or 3 or 4 possibilities. That's all. I just want to show you how the modular transformation, modular invariance implies some such condition, some such GSO type projection. And that I can do without doing any calculation. So just by drawing pictures, I think one can do that. So let me just do this, that part here, before going on to the interpretation of parameters. Okay. Now, so remember in the fermionic string, I mean, all this GSO projection appears in the fermionic string, right? So let's look at the fermionic string, or the left moving part of this hyperotic string. Fermionic string, we had 2 sectors, Navier-Schwarz and Ramond. Now, what was the definition of Navier-Schwarz sector? You had the definition that psi of sigma plus 2 pi is equal to minus of psi of sigma. So it's anti-periodic as you go around the sigma circle. Sigma is the closed string, the coordinate, the spatial coordinate of the closed string. And Ramond is given by just choosing the plus sign. So this was the difference, right, between the 2 cases. Now suppose I want to look at the partition function for the Navier-Schwarz sector at the one loop level, torus level. So this is the torus diagram, which we have seen yesterday. So you have 0, 1, and tau plus 1 here. So this was the parallelogram which was defining the Bolshevik torus. And say I want to compute the trace, I want to look at the trace over the Navier-Schwarz Hilbert space of q to the L0, q1 to the L0 kilodimes. So I want to look at this trace. But now, so what we are doing, we are propagating the string in the Navier-Schwarz sector and propagate it up to that point and then trace over, right? But I will put a minus sign here to indicate that here I have an anti-periodic boundary condition. In other words, when I take the fermion from here to there, it picks up a minus sign, right? That was the Navier-Schwarz definition of Navier-Schwarz sector. What about this side? This is also a circle, right? Because this identified, these 2 points are identified. So as I move this fermion from here to there, question is what is the boundary condition? There are 2 possibilities. I can have either plus sign or minus sign as I go along this circle, right? Okay. So let's suppose I start with a minus sign. Suppose I started with a minus sign. So I look at this particular sector. By the way, these are called spin structures. On a torus, you have 4 possible spin structures for the fermions. You can have plus minus here and plus minus here independently. So altogether 4 spin structures are there. When you look at higher why 4? Because you have 2 independent cycles on a torus. You see, you have like this here. There is one circle like this, other circle is like that. Which is, when I say these are non-trivial cycles because you cannot shrink them to a point, right? Without breaking it, you cannot. So there are 2 independent non-shrinkable cycles. Any other non-shrinkable cycle can be written as combinations of these 2. So around each cycle, you have a possibility of having antiperiodic or periodic boundary condition. So you have 2 for each cycle. So you have 2 to the power of 2. But if you look at higher genus space, say something like this here. So I have 3 of these cycles and 3 of those cycles. So altogether, if you have a genus G surface, so G handles are there, then you have 2 G cycles, and you have 2 to the power of 2 G spin structures. So the number of spin structures exponentially grows up. In any case, we are focusing here. Okay, so we start from here, and I look at the modular transformation, tau going to tau plus 1. Remember, we have to make sure that the theory is invariant under such transformation, these 2 transformations. When I do this transformation on this sector where you have a minus antiperiodic here and antiperiodic there, now what happens? At tau plus 1, see, the tau has gone to tau plus 1. So now I'm looking at this parallelogram. But to reach there, so I want to ask, what is the boundary condition for the fermion when I move it from here to there, right? But when I can go from here to here by first going from here to here, and then going from here to here. Okay? But in each of these processes, you pick up a minus sign. Because as you go from here, you get a minus sign, and this cycle is the same as that cycle. So as you go from here to here, you again pick up a minus sign. The minus times minus is plus. Okay? So you get a plus sign there. So what this means is that if I had just stopped myself, I had just included the minus sector, there would be no way to be modular invariant, right? So I need to also add the other piece. So I need to have, so this already tells me that I certainly need to have this structure here. I need to have both minus and minus plus, okay? With some sign, with relative sign. Some relative coefficient which may be determined by the details of this transformation. But for sure, I need to include both of them. Otherwise, there is no hope of modeling. So what is the meaning of including both of these? You see, suppose I call this as just a trace. This guy is simply, this R is simply trace over the Schwarz sector. Now look at this. How do I go from here to here? What I have done, I have just flipped the sign along the time direction, right? But that is equivalent to inserting a -1 to the F operator. If you insert a -1 to the F operator inside the trace, what is it going to do? It will, so if I insert inside here a -1 to the F, that is equivalent to flipping the sign of the boundary condition for the fermions. Because every time the fermion propagates, this operator gives you an extra minus sign, right? Because -1 to the F is a fermion number. So F is equal to 1 for each fermion, and for boson it's 0, right? For X's it is 0, and so F is the fermion number. Well, it's a discrete fermion. It's a fermion number. So for each psi, it gives you an extra minus sign. So on top of this minus sign, which was already there, I have an extra minus sign. So the combined thing becomes plus. So the sum of these 2 terms can be written as simply 1 plus -1 to the F, plus or minus. That depends on the details of the precise coefficient which you need to put. Okay. So you find this. But this is exactly the GSO projection, right? With a minus sign. And actually, you see when you look at the detail, there's a minus sign. This is exactly the GSO projection which removes the tachyon.
Sorry, I got lost. Could you explain again why do we need this other?
The other sector coming from this. You see, so we got invariance under tau into tau plus 1. Right? But if I start from my original amplitude, which was -1 so minus path integral, and I make this transformation, but geometrically you can see what does it do? You have gone from here to there. Right? Tau has gone to tau plus 1. So now my parallelogram is this parallelogram. Right? Which of course is nothing, it's the same basis of the same lattice. Right? But nevertheless now, this is my new tau, right? When I make such a transformation. But if I have the initial boundary condition was this minus here and minus there, this is the same as that because these two cycles are the same. This is identified. Right? So you know you can ask what sign the fermion gets when you move from here to there, right? Because that's my new tau, new cycle here. So to go from here to here, I can go from here to here first, and then after that I go from here to there. But in each process, it picks up what? The minus sign. So minus times minus becomes plus. So when you go from here to here, you get a plus sign. So there is no way, if I just stick with the minus signs, the partial function cannot be modeled invariant, right? So you need to include both these terms, but then I try to interpret that this term is the same as starting from here, but putting an extra insertion of an operator, -1 to the f. So you need a particular combination, and it turns out that's so to find the precise combination, you need to do a little bit more detail, not just picture. I mean, these are just pictures, no? But you need to look at what is the object here and do the transformation tau into tau plus 1, and you find the minus sign. Actually, that minus sign is nothing else. That comes from the you remember the Levi-Schwarz sector. The intercept was -12. Just because half integer there, you pick up a minus sign, extra minus sign. That's why you pick up a minus sign. That's exactly the Gilson projection which removes a tachyon. That's one thing. But we are not finished yet. We have to also look at tau going to -1 over tau. Right? But tau going to -1 over tau is exchange of sigma and t. The exchange of the two cycles. But when you exchange, so already we have concluded from this discussion, from the first one, we have already concluded that we need both of these terms. Right? Now when you do tau, when you exchange sigma and t here, nothing happens because both have minus antiperiodic boundary conditions. So this diagram goes back to itself. Right? But when you look at this one, when you exchange sigma and t, this will go over to another diagram which will be like this. Right? So now you see, this was my sigma direction, that was my time direction. Now, when you exchange the two, so now you have this boundary condition. But this means that I'm considering strings where the fermions are periodic, right, along the sigma direction. But that's exactly the H-Ramon, the Ramon sector. Right? So this is telling you that it's not enough to just stop with the Levi-Schwarz. You need to also include the Ramon sector. So these are the three things here, three objects here. Three things here. And so that this is telling me that I must also include. This is not enough. This will not give me modular invariant object, but I also need to include the H-Ramon and compute this partition function, appropriate partition function there. So all these three sectors. Unfortunately, we cannot get. Unfortunately, the last sector which remains is the plus. Right? I told you there are 4 sectors here, 4 possible. This sector is still there, but this cannot be obtained. This is completely modular invariant by itself. So this is modular invariant by itself. By itself. Because you can see, if you go take tau to the tau plus 1, so this point moves there. The boundary condition here is the product of these two boundary conditions, but plus times plus is still plus. And similarly, when you exchange sigma and t, again nothing happens. Plus remains plus. So this is invariant. So you don't. So actually, these 4 sectors form into 2 different orbits under the modular. These 3 form one orbit, and this last one is by itself. This stays by itself. So you don't see at this point the need to include this, because this would mean, what would this do? this will again be insertion of -1 to the f. So that will be the GSO projection on the Ramond sector. And remember, that was also crucial to get the correct supersymmetry. The projection on the Ramond sector, GSO projection on the Ramond sector, picks out a definite chirality of the Ramond vacuum. Right? Ramond vacuum, to begin with, you started with the both chiralities. But this GSO projection is what picks out one particular chirality. So this is separate by itself, and in fact, that also tells you that, you see, here I was forced to choose a particular GSO projection because these two are related, and that is what gave us the precise sign here, minus sign. On the GSO, on the right, on the Ramond sector, you can have both 1 plus or minus 1 to the f. It doesn't matter. Which means I could choose both chiralities. Say plus sign corresponds to left chirality, minus sign corresponds to right chirality. This is the reason why we have both possibility type 2A and type 2B. Right? That was exactly the difference between type 2A and type 2B. Right? The choices of the chiralities. So all these are there. Yeah. So this is the reason. So in some sense, this at least makes it less unnatural, the GSO projection. Right? It is dictated by modular physics, but not quite. I have cheated a little bit. Okay? Because you see, this modular transformation, you cannot talk of modular invariance. You cannot talk about independently on the left movers and right movers. After all, the partition function has both q to the L0 and L0 tilde. So it has both the left moving part and right moving part. What we want is actually combined action on the left and right is modular invariant. But here, to get the GSO projection, you remember the GSO projection you do independently on the left and the right. Right? Certainly, this is one solution. You can do the GSO projection, which was given by Carmen in last week. That definitely gives you a modular invariant answer. But unfortunately, there are a few more possibilities. Okay? And those possibilities are non-supersymmetric. Because the GSO projection is combined in the left and right. It's a kind of diagonal GSO projection. So it has tachyons, it is not supersymmetric, and those are called, I think, type 0A and type 0B models. Okay. And similarly, in heterotic theory, when I discussed all of these things, I was assuming implicitly that the part which was, we were focusing on the lattice part, the lattice part in all this discussion. So I assumed that the rest of the part, the Fock space part, was modular invariant by itself, right? But in reality, we don't need to do that. What we need is only the combined action, right? So there are ways to couple the GSO projection here with the action on the lattice. Okay? And so you get a few more models. I don't remember exactly, but those are non-supersymmetric models. Okay. I think there's a model which has O16 plus O16 gauge group, and I think there are a few more examples like that. But they're not supersymmetric. So the conclusion from this discussion is modular invariance is very powerful. It picks out exactly the right ones that we have been doing so far, but it gives you a few more finite number of more possibilities which are non supersymmetric.
But I didn't understand why -1 to the f, because we were talking about fermions on the way.
Yeah, fermions. But so the question is, it's like so you are inserting. So if you insert a -1 to the f operator in the operator in the partition function in the trace, what is it going to do? If you think about it, it's some state. You start with some state psi. You apply -1 to the f, and then you evolve it. So what it will do is it will check what is its fermion number, right? And if its fermion number is odd, it will give you a minus sign. And if fermion number is even, it will give you a plus sign, right? So now consider a single fermion state, or just look at the wave function, not in some kind of Hamiltonian basis, but just the coordinate basis. So x basis and sigma basis. These are the basic variables that you're integrating over x and psi, x and psi. Right? You're integrating x and psi. These are the objects which you're integrating over, right? So you can consider the wave functions which are kind of just the psi eigenfunction, which are like like in the quantum mechanics you do. You just look at the position eigenstates, right? Here the eigenstates will be the x eigenstate and psi eigenstates. So when you look at this psi eigenstates, you are evolving it around it, and psi just picks up a minus sign by the time it reaches there, and then you take the trace. Okay. Then you identify the two psis there. But it has already received a minus sign because of this operator. I mean, you have to take the trace, which means, suppose I had started with some sign, some value of sign here. You arrive there, and then you identify the two sides. I mean, anyway, maybe we can discuss. This is just a standard formula, I mean, going from path integral language to the operator language. You can insert some operator to change some boundary condition. There was something else I wanted to say. No. I mean, this was just to show that GSO was not so ad hoc.
Why did you take out the plus sign in the NS section?
The what? Sorry,
The
what?
plus sign. Initially we have 1 plus minus. And
Yeah,
minus
that
1.
turns out, because in order then to see the precise sign, relative sign between that, you see here, I mean, here I'm just looking at the boundary condition, right? But now we have some answer. When you compute trace q to the L0, q bar to the L0 tilde, in this sector, in this particular sector, we will find some particular function of tau and tau bar. Okay. Now you ask the question, so you can directly do the tau going to tau plus 1 transformation. And you find, and you try to see how is that compares to what you would compute here. You find that there's an extra minus sign. And the reason is not difficult to understand, because you see here, remember what was L0? L0 was you had this n minus half, apart from other stuff. But the GSO projection, there was a minus half. In the Davis-Schwarz sector, there was a minus half. So when you take tau going to tau plus 1, you see that this minus half gives you an extra minus sign. Okay? That's the reason for the extra minus sign, the relative minus sign. So it picks up a definite sign. Because you have an answer here, you have an answer here, and then you just ask the question, what leaves this invariant? What combination I should choose that it leaves invariant, and you find its minus. But it's basically from that. It's this minus, this minus. I mean, this minus half is what gives you the tachyon, right? In the fermionic Davis-Schwarz sector, which you kill by GSO projection. And that's exactly that. With a minus sign, it's kill sign.
You were talking about chirality there.
From this Ramon sector. Because Ramon vacuum is a spinor of SO8, right? SO8 is a transverse group. So it's a spinor of SO8. And the spinor, I mean, it can have both chiralities, right? So if you have both chiralities, it's 16 dimensional. To get supersymmetry, you need exactly 8. Right? Because you have 8 bosonic freedom in the transverse coordinates, transverse directions. So you need 8 exactly. And that is obtained by a GSO projection. In fact, the minus 1 to the F operator exactly, when you apply on the Ramon sector, it gives you one sign for the positive left-handed fermion and opposite sign for the right-handed. That's what it is. Okay. Now let me go back here. Sorry. I want to discuss, spend only half time for heterotic. Okay, very quickly let me just mention what is the interpretation of the moduli, and also perhaps this will shed some questions. I think there have been several questions in Clifford's lecture. What is Wilson line? Maybe again, so I will give an answer, which is basically the same answer as Clifford. Okay, so now let's think in terms of, let's try to understand the physical meaning of these parameters. Right? At this point, it's very abstract. It is just some parameters which enter in the definition of lattice, right? But what is the physical meaning? And the physical meaning you can understand. So I started with 10-dimensional theory in hydraulic string. And so what are the massless fields here? So let me put here the index Mn. So Mn are all the 10-dimensional indices. Right? So M goes from 0 up to 9. These capital letters go from 0 to B, Mn, and the Dirac and the gauge field. These are the bosonic fields. Right? These gauge fields are in either SO32 or E8 cross. So these are the boson fields. That's all. And there are fermionic powers. But when we talk about the parameters which will come in the compactification, you're always talking about the bosons. Because you don't give vacuum expectation value to the fermions. Vacuum expectation value you give only to the bosons, right? So this is enough for us. So what happens when I compactify on a d-dimensional torus? Well, you just split this indices in terms of the space, the non-compact Minkowski part, the 10 minus d-dimensional Minkowski space, which was, remember I was labeling my mu and nu here. This was labeled by I and j, etc. Right? So this GMN splits into several terms here. One is the G mu nu. Then you have G mu I. So one index in the torus direction, one index in the remaining space, and then finally you have Gij. Right? So from the point of view of the Lorentz group which acts on the Minkowski space, this is the metric. This is a symmetric tensor, the metric. This is a vector, right? And how many vectors are there? There are as many as the I. There are I index runs over D, so there are D gauge fields. D gauge fields. D U1, I mean U1 to the D. See? Now these are scalars, right? Because there is no mu index. So from as far as the Lorentz group of the space is concerned, these are the scalars. How many scalars are there? This is symmetric, right? So this is simply D times D plus 1 by 2. That's the number of parameters here. Right? Now you can choose any value for the G, constant value for the G. Constant value of the G will keep the space still flat, right? So that many parameters are already there in your compactification. That's a geometric parameters, which appear in just the geometric torus, common torus. What about this BMN? Again, you can decompose B mu nu, B mu I, and Bij. So if this is the antisymmetric tensor in this space. B mu I again gives you U1 to the D gauge fields. And Bij, these are scalars, and that number is, since it's antisymmetric, it's D times D minus 1 by 2. Right? And these are the parameters. So these are like turning on fluxes of the B field on the torus, in the d-dimensional torus. Right? Constant flux, not the field strength. B is the potential, right? Field strength would be the derivative of the B. So this is a very trivial flux. I mean, these days, a lot of people are doing compactifications with fluxes of the field strengths. I'm not doing that. This is the flux of the potential, constant flux. So the field strength is 0. Field strength is the H. H is the dB, right? That is the field strength. Field strength is 0 because there is constants. Okay. So finally, dilaton stays there as it is. The dilaton is not part of the compactification. This was already the string coupling constant in 10 dimension. That stays as it is, right? That's still there. This is a scalar, so that's still there. What about the AI? This is interesting because so again, it splits into A mu and AI. This is a gauge field. So whatever your gauge group was, that will be that gauge group will appear also here, in the lower dimension. But this AI are scalars, so in principle I can give vacuum expectation value to them, right? But you see, I want to consider the flat space because this whole discussion was on the flat space. I mean, the torus was flat. We don't want to turn on some stress tensor there because if I turn on stress tensor, then the space will no longer be flat, right? So I want to do it in such a way that there is no. This is the reason why I didn't turn on any field strength here, right? If I turn on some field strength here, then you'll have a non-trivial stress tensor. So the flat metric will not be a solution, right? That's in the equation. So this is flat, so there is no stress tensor coming from here. So I also want to look at something which is flat here. Field strength is 0. So I will take this to be just constants. Although you can relax it because after all, it should be constant up to gauge transformation. So what we really mean is a Holonomic, but let me not. So it's some constants. Okay? So I just choose 3 constants. But how many of these I can choose? Well, naively speaking, you will think that this is D, I is D, but the gauge group, this index A here, right? This index A runs over the Lie algebra of this group or that group, right? The dimensions of these groups, both the dimensions of both of this group is 496. Well, you can compute this 32 times 31 by 2 is that. And the dimension of E8 is 256. So 256 plus 256 is
248.
no, 248. So 248 plus 248 is 496. Okay. So that's 496. So one may naively say that, well, this A can be from 1 up to 496. You know, that's a huge number, 496 times D. But we are finding only this quantity. You see, what we have is D squared is already been taken into account. You just add these two, this and that. You see, when you add that up, plus 1 and minus 1 cancels, and you get D squared by 2 plus D squared by 2, which is D squared. So we have already taken into account this. What is remaining is 16 times D. So it's not 496 times D, but what we want is 16 times D. But what is the reason for that? I mean, 16 is what? 16 is the Cartan, dimension of the Cartan subalgebra of these groups, right? The Cartan subalgebra of X22 is 16 dimensional. Cartan subalgebra of E8 is, as its number 8 suggests, is the 8 dimensional. So E8 cross E8 is 16 dimensional. Cartan subalgebra, right? So that 16 is a Cartan subalgebra, the dimension of Cartan subalgebra. So for some reason, we are allowed to turn on, give random expectation value to only the A's in the Cartan subalgebra. That's what one is saying. What is saying. And the reason is very clear, because remember, in 10 dimension, so in 10 dimension, we had the field strength Fmn squared. That was a term in the action, right? With some coefficient. I'm not interested in the coefficient. This was what it was, right? Trace Fmn squared. That was the part of the action in the millisecond, right? But now again, let's split that. So this will go over to F mu squared, trace of F mu squared, plus trace of F mu I squared. And then we'll have trace of Fij squared. Now so what is F mu I? F mu I, or in general, what is Fmn first of all? Let's write down Fmn. Fmn is Dn An minus Dn An plus the commutator term An, because remember this is non-abelian groups, right? So the algebra is non-abelian. So you have the commutator An, where I've written this is the matrix now, right? So this Am is simply equal to A times the generators, the TA of the generator. So this sum. So this is the Fmn. So F mu I, so now let's specialize to the case F mu I. What is F mu I? D mu AI minus Di A mu plus the commutator A mu AI. Now we are taking all of these fields to be independent of the internal coordinates. So we are looking at the zero mode, not the Fourier. I mean, of course, you make a Fourier series expansion, but we're looking at the zero mode in the torus directions. So this term vanishes, and we combine these two things. This is nothing else but the covariant derivative of the AI, which are scalars. So this term, F mu I squared, just gives you the covariant derivative, the gauge covariant derivative of the scalars squared. So that's a kinetic term for this. It's in the gauge covariant way. But the more interesting thing is that Fij squared, I mean, this is what we are focusing on for our purposes. So what is Fij? This is Di Aj minus Dj Ai plus the commutator Ai Aj. So this is what it is, right? Now look at this. We said that we are going to take the zero modes, constants, right? So of course these two terms are vanishing because they're derivatives, right? So if Aj and Ai are constants, these are zero. However, this is not zero in general. There's no derivative here. So even for constant A's, this may be not zero. So what you find is that for the constant A, this gives you the commutator of Ai Aj square trace. This is a non-zero potential, right? In general, if I just arbitrarily choose some AI and AJ, constant AI and AJ, you're going to get some potential energy. And then the flat space will not be a solution, right? So you want to make sure the potential energy is zero. So you are choosing the expectation values in such a way that the potential energy is zero. But this is the sum of the squares, you see. There's a summation over ij. Right? There is for each fixed ij, there is a square here. And these groups are unitary groups. I mean, these are Hermitian or anti-Hermitian matrices. So these are definite, these are positive definite. Each term is positive definite, right? So the only way it can be zero is if this is zero for each I and j, right? So that means whatever choice I should make here, I better make sure that the commutator of AI with AJ for all I and j is zero, for all I and j. Of course, I and j go from 1 to d of them, right? But that exactly tells you that this A must be the Cartan subalgebra. That's in the maximal commuting subalgebra. This is the Cartan subalgebra. So you have only 16, because Cartan is 16-dimensional. This is 16-dimensional Cartan subalgebra. So these indices can only run over the Cartan direction. 16 times d, and that's that. So that's a physical interpretation of this parameter. So they're really expectation values, very trivial expectation values. No, there's constant expectation values of fields, but nevertheless, that's what it is. Any question?
Yeah, probably is my fault. I thought that the gauge fields only appeared in theories with open strings.
I mean, here, yeah, I mean, that is certainly one way to get the gauge field. But in heterotic, we already saw that this gauge fields, right? So this, let's say in the closed string theory, you're getting these gauge fields. Yeah. Actually, that brings to me, in fact, I forgot that I promised I would talk about the cellular radius. So let me just mention that. That is another, you see, not just that, you see, not only already here, you see, you have the original gauge fields in 10 dimension, but you also have the Kaluza-Klein gauge fields. This is the Kaluza-Klein gauge fields, right? So when you compactify, in general, there can be additional gauge fields, right? So, okay, this was as a toroidal compactification. So in general, Kaluza-Klein gauge fields will be given by the number of killing vectors in the internal space. In the d-dimensional torus, there are d killing vectors. But in some other space, maybe there are some other number of killing vectors. But nevertheless, always it will be equal to the killing vectors. And if the killing vectors satisfy some non-abelian algebra, these gauge fields that you will get will also satisfy the same algebra. But here it's all abelian. And these BBOIs, these are additional. These are kind of stringy in some sense, because in field theory, normally you don't have this antisymmetric tensor. Right? But okay, if you had this antisymmetric tensor, by Kaluza-Klein reduction, you will have this extra tensor. But there is another peculiar way the gauge fields can come, and that is what is called really truly stringy version of the appearance of gauge field. And that's what appears at the cellular radius. So maybe I should just give it. Although this is taking me away from the S-duality, completely away. Maybe I can talk about it in the discussion session. But not today. Today is no discussion session. Okay, maybe tomorrow if someone asks me, I can, because it's a bit, I'm sorry, anyway, now what I can start. No, okay, let me start the discussion of dualities, and come back to this the circular radius. Please remind me in the question session. Then I will come back to that. Because it's interesting, because you see this really stringy. The appearance of an extra gauge field is really stringy. Gauge, master's gauge. Because this is the action, this is part of the action. Yeah, because if it has not vanished, you will get some potential, non-zero potential energy. And then the flat solution will not be a solution anymore. Okay? You'll have either implicit or implicit solution. So let's now summarize what we have, so far what we have ring, you have the type 2A, type 2B. So these are n equal to 2 theories in 10 dimension. Then you have type 1 and heterotic SO32. Oh, one thing I should, okay. There are so many things, heterotic here plus here. You see, in 10 dimension, there are 2 different theories. I mean, to begin with, there are 2 different theories. But once I compactify on a circle, on any dimension, on a torus, for example, a circle, even b equal to 1, we just compactify in a circle, we just get this moduli space. I mean, there is only, as we said, there's only one lattice up to this rotations. So what this means is that, I mean, it doesn't matter where you started with in 10 dimension. Once you compactify down to even on the circle, these 2 theories are related to each other. They're not distinct theories. You can go from one to other by moving along this moduli. So, in 10 dimension they're different, but once you come to 9 dimension on a circle, they're already related. 2A and 2B also, once you compactify in a circle, there is no difference between the 2. Because you see the difference between these 2 was on the chirality. Type 2A was non-chiral, type 2B was chiral. But once you come down, chirality exists in the even dimensions. The notion of chirality exists in even dimensions. Once you go to a compactify in a circle, you come down to 9 dimensions. There's no notion of chirality. So both of these theories give the same spectrum once you come down. And more precisely, actually you can see what is the precise relation between the 2. It's actually a T-duality. This relation is a T-duality relation. In other words, if I compactify type 2A theory on a circle of radius r, that is equivalent to a type 2B theory, the compactifier on a circle of alpha prime r. This is a more precise dictionary. And you can see that why that is happening. I mean, it's important to understand that type 2 and type 2B are related by some T-duality because if you look at the Ramon forms, okay, what is the T-duality? T-duality, suppose I do a T-duality on the, say, 1th direction, say, ith direction, or let's say, the 9th direction, to be this specific. So let's say I compactify my space of the x9 is a circle, and I just do a T-duality there. So of course, alpha r goes to alpha prime over r, T-duality, but it does many other things too. There are several other things happening. So what is happening? First of all, the G mu 9 exchanges to B mu 9. So mu is the remaining, the Minkowski directions, the 9-dimensional Minkowski direction, and this is the extra circle, 9th circle. This is the small I, what I was calling small I. So I'm just looking at B equal to 1. Just a simple circle. So there's an exchange here, and you see why. Because remember, one way to quickly to see is that Kaluza-Klein momentum is the charge with respect to G mu 9, and the winding mode is the charge with respect to B mu 9. Right? But the T-duality exchanges the Kaluza-Klein momentum with the winding mode, winding number. Right? So therefore, it must happen that G mu 9 and B mu 9 are exchanged. Okay? More very explicitly, you can see the following: G mu 9. The vertex for G mu 9 is what? Dx mu, dx9, plus, because G is a symmetric part, right? Plus the dx9, d bar, x mu. So this is the left movers and right movers and so on, right? Whereas what happens to B mu 9 is just with a minus sign. So this is the G mu 9 vertex, and the B mu 9 vertex is dx mu, d bar x9, minus dx9, d bar x mu. These are the vertices for me. Now, when you do the T-duality in the x9 direction, you have seen that T-duality can be thought of as a parity transformation on the right movers. You see, because the x right goes to minus x right. Right? That was, I think you have just seen that in many discussions. Maybe Clifford has talked about it, right? So T-duality in the 9th direction is the same as a parity transformation, but not a geometric parity transformation. Geometric parity transformation would be acting on both left and right. It's not geometric. It acts only on the right sector. Parity on the right sector. So in other words, d bar x9 goes to minus d bar x9. But dx9 stays dx9. And this parity is only acting on the ninth direction, doesn't do anything on other directions. And now you can see, so d bar x9 goes to minus d bar x9. So this picks up an extra minus sign. Okay. Whereas this doesn't. So you get a relative minus sign between the two. And so the g mu 9 goes to d mu 9. So this is very explicit. I mean, there are many ways of seeing it. Already from the fact that this closure is a charge with respect to that, and binding is a charge with respect to that. But I mean, of course, everything has to converge. Otherwise, the thing wouldn't make sense. So that is how it acts. So this on the G mu 9. That is all. Only this changes, not other guys. G mu doesn't change. G mu stays G mu. G mu stays. The other thing that it does in the Ramon forms. So if I started with a Ramon form, some I don't know, let's say Cn, some n form potential. And so it will have how many? It will have some n indices, right? Because the n form. So n indices. Now there are two possibilities that all of these indices may be lying in the 9-dimensional space. They could be all the mu type of index, or it could be that one of these indexes is 9. Right? So there are two possibilities. It can be either Cn, say mu 1, mu 2, all the way up to mu n minus 1, and then the last one being the 9 direction. All the other possibilities, Cn, mu 1, mu 2, all the way up to mu 1. So all of them are in the Minkowski, 9-dimensional Minkowski. Now when we do the t-duality so along the x9 direction, what happens is that this guy goes to its n minus 1 form. The 9 gets removed. Mu n minus 1. Whereas this guy goes to Cn plus 1 form. So you have all of that. And you add also an index 9. This is what happens. And it is important that that happens. I mean, if this had not happened, there would be a problem. Right? Because, I mean, what is the object which is charged under that? Well, this is a brain which is wrapping along these directions, which is in these directions. A D brain, which is in this direction, whose longitudinal directions are that. Right? So that will couple, if you have a brain which is along these directions, it will couple to this n form with these indices. Right? Now, when you do a t-duality in the 9th direction, right? You see, so what it means, in this case, this is a longitudinal, 9th is in a longitudinal direction, which means it was a Neumann direction, longitudinal to the brain, because brain world volume is living on these directions, right? So it's longitudinal to the brain. So it's a Neumann boundary condition. When you do t-duality, that Neumann boundary condition becomes Dirichlet, right? So it becomes transverse. So that brain, so 9th direction becomes a transverse direction. And that's exactly, that will couple to this form. Right? So if this had not happened, if this transformation had not happened, the whole picture of the D brains would be inconsistent. Okay? The same thing here. If you started from here, so you think of a brain whose world volume is in this direction. So 9 is transversal, 9 is not in this direction. So x9 is Dirichlet. You do a t-duality, it becomes Neumann. So it becomes part of the world volume. Okay? So this t-duality is crucial. But once again, I mean, you can check it explicitly by writing down the vertices for that. Just like here, I showed you that you can understand that also by looking at the vertices. The same thing you can do here with the vertices. But I don't think Ramon vertices have been introduced, probably not. Right? So I'm not going to talk about it. This will just complicate the discussion. So, but if you see the Ramon vertex, do the t-duality, which is exactly this, what I mentioned, parity transformation on the right sector. You implement that, okay? But now you see this parity operator will be acting on the spinors. So you have to find the representation of the parity operators of the spheres. So, but that's easy to find. You do that and you find exactly these transformations. So that's, besides this, something else also happens, and that's the coupling constant, the phi, the spin coupling constant. You see, the action, that will be my last part. You know, but the action was, sorry, the action, effective action, low energy effective action. Low energy effective action. Was schematically, I'm not going to be very precise about it, something like d times x, root g, g is a metric, in the string frame, e to the minus 2 phi, the dilaton, and then you have r plus d phi square, with various coefficients. I'm not worrying about the coefficients. Actually, I will not worry at all about it in the whole discussion. Plus h square, h being the field strength of the Lewis-Schwarz 2 form. This is the Lewis-Schwarz sector, and then you have the Ramon sectors, which are some Cn square, without the Fn square. F is the field strength of C. F n plus 1. F n plus 1 is dc square. This important point that I think Clifford also mentioned, that this doesn't come with the dilaton factor. Naively, you would have expected that, because this factor, as he said, just comes from the fact that all of this is a tree level effective action. So tree level effective action, how do you compute this? You compute it, one way to compute it is look at the sphere, which is a tree level worldsheet, and start inserting various vertices, okay, various operators, and then compute the scattering amplitude, and then try to write down what action would reproduce that. But since all of this calculated the sphere comes with the Euler characteristic chi is 2 minus 2 and the genus G. Okay. For the sphere, there's no handle, so chi is 2, and you find that this factor is simply e to the minus chi. This factor, the chi, so e to the minus chi. So that's one. So, but this also, you see, I mean, this also is a tree level term. So why not? Why there is no such factor? And it turns out, I mean, there is, at least I don't know of any simple explanation for this. It is just that you compute it. So, I mean, if there was an e to the minus 2 phi factor, then you should have some amplitude involving f, and the dilaton. And you find it's not there. So this term is not there. And very roughly speaking, the thumb of rule, or rule of thumb, what's called rule of thumb, is that every time a Ramon is as if every time a Ramon vertex is inserted, it already comes with a factor of e to the phi. Okay. So I mean that rule works. With that rule you can. So since there are two Ramon fields here, they come with an extra e to the 2 phi, which cancels e to the minus 2 phi. And that works for also higher terms. I mean, but it's not a very simple way to understand it. I mean, there is work by, I think, there's somebody called Dmitry Polyakov. He's not the A. Polyakov, he's the son of the famous Polyakov. Who has written some papers in the 80s, late 80s, late 80s, who discusses this issue. And okay, I haven't read these papers carefully, but he claims that he has some understanding of that, from the fundamental principles and why that happens. Okay, so this is what happens. And now let's look at, and of course, this is for the type 2 side. If it was not type 2, but heterotic theory that we're doing, it will be trace f squared. Sorry, this is now, I mean, this f is the Ramon. This is in the type 2 case. This would be the type 2 case. But let's forget the type 2. Let's look at no, actually we're looking at the type 2, sorry. We're looking at the type 2. So, okay, let's just keep that. F squared. 1 more. But keep that also in mind. That suppose instead of this I was discussing heterotic, I'll have trace f squared. This will be the EA cross EA to SO32, right? Times e to the minus 2 phi. Because that factor is the same. This is no difference. E to the minus 2 phi is there. This is not a Ramond vertex, so there's no problem with that. Now, if I make a t-duality transformation, so what is going to happen? I mean, so first of all, let's compactify this. You get here d10x, d9x, and the root g simply becomes, so I say I integrate the circle direction. This becomes, root g becomes, okay, there's a dx9, and root g becomes the root g mu r. And then the 9th direction is circle, so it is radius r. This is not the curvature, sorry. Let me put here radius r. This radius r of the 9th direction, x9 radius. I don't want to use capital R because capital R I'm using for the curvature scale. So what you need to do is to, do some, because this will change the action, right? You know, I have an extra fact. If I change gamma to, this R, the 1 over R, then this factor is going to change, right? Action will not be invariant. So what you do is you have to make a transformation on the phi to compensate for that. It's something like this. Phi goes to phi plus, I don't remember exactly the coefficient, but you can work it out from this requirement, something like log R. Some such things will work out, just to compensate for that. Because if you shift by this log R, it will give you some R to some power. This should cancel, this should cancel. So this is basically the transformation. T-duality does a lot of things. It makes, of course, the radius to 1 over radius, but also it acts on the G mu 9 to B mu 9, then it acts on the Ramond field, and also it changes the Dirichlet by a shift. All this will play an important role when I discuss the S duality. Well, maybe I should be strong. Okay, here I'm thinking all the fermions will be or everything, the closed one. Because otherwise you will break supersymmetry. Because whatever you want to do, you want to have supersymmetry. Because if you have to put anti-periodic boundary condition along some direction, all the fermions will become massive. Whereas if you want some baseline supersymmetry, you want to have single boundary. So these are very trivial. Maybe here the analogous thing is because particularly this will be important for Aramaria's lectures, because there she will think of this xi, this capital Xi that I was talking about, in terms of fermions. And those fermions will be transforming in the vector representation of SO32. Right? So if I give some Cartan expectation value for Cartan field, those fermions will become twisted fermions, right? Twisted by the polynomial. So that will appear.
Any other questions? Okay. Thanks again.